Hi everybody. When we do chemistry reactions, it turns out that it's very rare that we get the exact amount of product that we're expecting. So unlike something like baking, where you're pretty sure what your results might look like, in chemistry there are all sorts of factors that can contribute to give us less product than we would expect. Sometimes more than one product can be formed, different types of products, we can just have experimental error through a variety of factors. So it's really rare that we actually see the exact amount of product that we might be expecting. So we're going to look at that today, and there are two things to keep in mind. One is called the theoretical yield. The theoretical yield is what we get from math, and it is basically the maximum amount of product that could be made if everything went perfectly. So based on the stoichiometric ratios, if everything went perfectly, the theoretical yield would go on the bottom of our percent yield formula, whereas the actual yield, which is what we actually get in lab, would go on top. So much like all of stoichiometry, we will need a balanced chemical equation to do this well. Pause the video, write yourself a balanced chemical equation for numbers 1, 2, and 3, and just a note, in number 1, use copper 2. So you want to use cupric. Hopefully you've paused the video, you've had a chance to write out all of the chemical reactions. I'm going to bring mine for number 1 back up. And let's write down what it is that we know. So we are given a piece of copper with a mass of 5 grams. As soon as we see that, let's immediately write it in. So 5.00 grams of copper. It's placed in the solution of silver nitrate, and then we produce silver with a mass of 15.2 grams. And I'm going to make this a different color for now. You'll see why that is in a second. And then we are asked, what is the percent yield of this reaction? So first off, you're going to notice that we're again given two amounts. And for those with a keen eye, you may remember that we said if you're given two amounts, that it is a limiting reactant problem. However, that's only if you're given amounts for both reactants. So this 15.2, this is not a reactant, this is a product. If it were a reactant, we'd have a limiting reactant problem. But it's not, it's a product. So now, if you're given two amounts, and one is a reactant, one is a product, that's really good indication that you're doing percent yield, in addition to the fact that it says what is the percent yield. That's another good clue, right? So this 15.2, this is the actual yield. So this is if the reaction happened in lab, and we actually measured our product, this is what we get, right? It's because it says when we actually do this reaction, the silver metal we produce has a mass of 15.2 grams. So that's what's in orange. What we're going to figure out with the green is how many grams of silver we can make from 5 grams of copper. So let's do that. Let's do some stoichiometry. We'll start with what we know. That's 5.00 grams of copper. Even before we do anything else, we know what unit has to go downstairs in the next fraction. We know that is grams of copper. We are on a journey over to grams of silver. In order to get to grams of silver, we must go through moles, right? To go from one thing to another, you have to be in the unit moles. So we know that we're going to moles on top. Where do we get the number of grams in 1 mole? Well, that comes from the periodic table. And for copper, that happens to be 63.55, straight off the periodic table. At this stage of the game, we know that moles of copper needs to go downstairs. We know eventually we're going to grams of silver, but before we can do that, we have to go to moles of silver. Where do those numbers come from? Well, those are the coefficients from the balanced chemical equation. So you'll notice there's a 1 in front of copper, and there's a 2 in front of silver. And then finally, we don't care about moles of silver, we want grams of silver. So on the periodic table, if you read it, it says that 1 mole of silver has a mass of 107.87. And that is grams of silver. And once we've done all of that, you'll notice that a bunch of things will cancel out. So our grams of copper, cancel, moles of copper, moles of silver cancel. We're left with grams of silver, and if you do this math, you will end up with 17.0 grams of silver. So what is that saying? That's saying if everything went perfectly and all 5 grams of copper reacted completely, the maximum amount of silver we could make is 17.0 grams. That's the very most we would be able to make. It turns out when we did this in lab, remember we only made 15 grams of silver. That was this actual yield thing here. So what we're going to do is some division. We're going to put our 15.2 grams that we actually produced over the 17.0 that we thought we could produce. When we do that math, we're going to get 0.894, but when you actually multiply by 100 to make it a percent, you get 89.4%. So you'll notice that we made 89.4% of the copper that we theoretically could have been able to make based on our starting amounts. Sig figs, we started with 3 in both the green number and the orange number, so that's why the black number is having 3 sig figs. All right, let's try again. We'll go a little bit quicker. We are producing this chlorobenzene in number 2. Here's what we're told. We're starting out with 36.8 grams of benzene. We're going to figure out if everything goes absolutely perfect, which product we can make. So how do we know which product we can make? Because it says the actual yield of chlorobenzene is 38.8. So that tells us that we're actually going to make 38.8 grams of this. But it also is a clue that we need to figure out how many grams of this we can make, because that's the product that we are given an actual yield for. So let's do that with stoichiometry. Let's start with what we know, 36.8 grams of benzene, which is C6H6. Before we do anything else, we know that grams of benzene can go downstairs. We need to get some moles because moles is our unit that allows us to go from one thing to another in a chemical equation. That number comes from the periodic table. You should try that on your own, but once you do it, you'll notice it comes out to 78.12 grams for every 1 mole. Now we can use our mole ratio to go from moles of benzene to moles of chlorobenzene. So moles of benzene we're putting on the bottom because it needs to cancel out. We're looking to get some moles of chlorobenzene on top, which is C6H5Cl. The numbers are the coefficients from the balanced chemical equation, which you'll notice are both 1s. So even though this does nothing mathematically, we need to do it to show how we got into chlorobenzene. And once we're in chlorobenzene, we know that moles of chlorobenzene can go on the bottom so that it will cancel out, and we ultimately are looking for grams of chlorobenzene on top, which again, you can go to your periodic table, put in 6 carbons, 5 hydrogens, 1 chlorine. When you do that, add them all up, you'll get 112.56. So conveniently, everything is going to cancel out. Our grams of benzene will cancel, our moles of benzene will cancel, our moles of chlorobenzene will cancel. When we do the math, we started with 3 sig figs, we'll end with 3 sig figs. It turns out to be 53.0 grams of chlorobenzene. Remember, this is our theoretical yield. This is how much we can produce if everything goes perfectly from our starting amount. So if all 36.8 grams of benzene react perfectly and we lose nothing, we will make a grand total of 53.0 grams of chlorobenzene. Turns out when we actually did this thing in lab, the actual yield we got was 38.8 grams of chlorobenzene, C6H5Cl. So if you do that division and you multiply by 100 to make it a percent, you will figure out that you made 73.2% of the amount of product that you thought you would be able to make. Which, by the way, those two percentages, 89.4 and 73.2, those are actually really good yields. Like if we were making some pharmaceutical drug or something as a medication, those are really strong yields in the chemistry world, even though on a test or something, maybe not our best. Let's look at number 3. So in number 3, we have 75.0 grams of carbon monoxide. So this was 75.0 grams. There's only one product, so we know we're going to have to convert to that product, and it says that the actual yield that we're going to make is 68.4 grams of methanol. So we're actually making 68.4, I believe. 68.4, good. 68.4 grams of methanol. And we need to figure out, theoretically, how many grams of that we can make. So let's do that. Let's take our 75 grams and let's figure out how many grams of methanol. So 75 grams of carbon monoxide. Again, we know before we do anything else, grams of carbon monoxide goes in the denominator. We need moles on top. Where does this number come from? Well, it comes from the periodic table. If you do that math and you add those together, you're going to get 28.01 grams of carbon monoxide for every 1 mole. This was a good move because now we have moles of carbon monoxide, Moles of carbon monoxide can be converted to moles of CH3OH, which is methanol, using our ratio, or our mole ratio from our coefficients, which is a 1-to-1 ratio. Again, it's important for us to write it though. And then we can finish by going to grams of methanol from moles of methanol using its molar mass. And if you add up all of those elements from the periodic table, you'll get a molar mass of 32.05 grams in every 1 mole for methanol. So again, conveniently, our units all cancel. Grams of carbon monoxide cancel, moles of carbon monoxide cancel, moles of methanol cancel. When you do this, sig fig wise, we started with 3 because it was 75.0. We'll end with 3. This turns out to be 85.8 grams of CH3OH that we could make if everything went perfectly. Remember, our actual yield though was let's find it up here. Our actual yield was 68.4 grams. So if 68.4 grams actually was produced in lab, and we thought we'd be able to make 85.8 grams, when you do that division, it turns out that you get a percent yield of 79.7% once you multiply by 100.